talking Schrodinger. I'm talking Laplacian eigenvalues, eigenfunctions, and operators. Yeah. And the wave function with the general anatomy of that wave function.
Hey there, my name is Eric, and I am teaming up with James and Brendan for the fourth time in a row, and we will be bringing to you different concepts regarding eigenvalues and functions, the Schrodinger's equations, and a couple more things in there as well. So yeah, let's just get right into it.
I'm going to be covering eigenvalues, operators, and eigenvectors. Before we talk about eigenvalues, we need to discuss what an eigenvector is. So in mathematics, an eigenvector is a non-zero vector that changes by a scalar factor when a linear transformation is applied. And then the eigenvalue is the factor by which the eigenvector is scaled. So a significant feature of a wave function is that the wavelength lambda can be extracted from the function as an eigenvalue. If we perform the appropriate mathematical operation on the wave function, then the answer is a constant that is multiplied by the original wave function, and the wavelength is a part of this constant, making the wavelength an eigenvalue. Having wavelength as an eigenvalue is very important because the wavelength of a particle is related to the momentum by the de Broglie equations. It's also important to note that energy is also an eigenvalue. Before we discuss what an eigenfunction is, it's important to know what an operator is first. And all that an operator is a mathematical operation that spits out a new function when applied to another function instead of, say, like a numerical value. So now that we know what an operator is, we can talk about eigenfunctions. So in mathematics, an eigenfunction of a linear operator defined on some function is a non-zero function. What makes an eigenvalue different from a normal function, though, is that when acted upon by the operator, an eigenfunction can only be multiplied by a scalar eigenvalue, such as wavelength lambda.
So for Schrodinger's equation, which is the Hamiltonian operator times the wave function equals the total energy multiplied by the wave function, we're able to find that it is possible to find the total energy of any quantum mechanics system if and only if an appropriate wave function is found that accurately describes said system. So the one-dimensional Schrodinger equation that we find is here, but that doesn't really relate into our third-dimensional point of view, and thus it can be derived using partial derivatives to be here. Using this, we can combine that with Coulomb's law, the Laplacian operator, and that equation will help us find an equation used to determine energy in atomic orbits.
So next up, I'll be talking about the Heisenberg uncertainty principle. It simply states that we cannot simultaneously know the position, the exact position, as well as the momentum of a particle in space. This concept actually, it also applies to the classical wave functions. So here I have drawn out one of those exactly, and if we recall this equation right here regarding momentum is equal to Planck's constant over the wavelength of the function there, both of those are finite values, meaning that the momentum is going to have a specific finite value as well. However, when we're talking about the position of this wavelength in general, it's infinitely long. Sure, it's just on the paper here, but if I had infinitely as many papers, it would be on all of the papers. And so that is why we cannot know the position as well as the momentum of particles, because they work the same way as these wave functions here.
Laplacian, or the Laplace operator, is denoted by the symbol of nabla squared, or an upside down triangle squared. The equation shown here is nabla squared is equivalent to the partial derivative of the three dimensions x, y, and z. What this means is that nabla squared is the square of a gradient where it is the divergence of said gradient. This value will only be 0 wherever the gradient is not changing. It is then used in wave functions using the formula here, where it is the Laplacian times the wave function is equal to nabla squared times the wave function. The Laplace operator can be found in the Schrödinger equation for an H atom, leading us to say that we have a way to find how atomic orbitals are in fact real mathematical solutions for the equation that combines Coulomb's law, Schrödinger's equation, and the Laplace.
So lastly, I'll be discussing what the physical meaning of what a wavelength actually represents whenever we're talking about electron density. So essentially, an orbital is a three-dimensional standing wave that surrounds an atom, and we use these to describe an electron's position. And so whenever we're discussing the electron probability density, we're actually looking at the likelihood of finding the electron in different areas of the wave function of the orbital. We like to use the particle in a box theory to help us understand this concept. So essentially, for the particle in a box model, all of the energy is entirely kinetic. There's absolutely no potential energy whatsoever. And what happens is a particle or electron can move back and forth in one-dimensional space. And as it does that, the kinetic energy will change depending on the wavelength of the wave function that it is on. So if we take this concept and then we expand it into 3 dimensions instead of just 1 dimension, and then we also square the wave function as well, that is equal to the probability density of an electron at any point around the atom in an orbital. And that is the physical meaning of a wave function.
We hope that you liked our explanation/mock tutorial of eigenvalues, eigenfunctions, operators, Laplacian, the uncertainty principle, and Schrödinger's equation on how it contributes to wave functions. Thank you.